Hello, my super chemists out there. This is Tracy Folks, and I'm ready for your last video installment from Unit 7 gas laws. And so we have talked about all sorts of gas laws, Charles, Boyle's, Gay-Lussac's, ideal. And I'm going to start this last segment with your notes here on Dalton's law of partial pressure. And you guys realize that all of your notes are on Schoology so you can follow along that way. Okay? So every year when I teach Dalton's law of partial pressure, I always just shake my head a little bit. Dalton gets credit for saying, if you have a container of gases and you want to know their total pressure, guess what you do? You add their individual pressures. Well, how easy is that? So all Dalton really said was that, oh, that one's not writing very well. Let's get a different marker. Here we go. He said that the total amount of gas pressure in a closed system is equal to the individual pressures of the gases. Well, duh, right? And so the example in your notes says you have a container with two gases. They have a total pressure of 5 atmospheres. So I'm putting that there. There's hydrogen in there and there's nitrogen. So the pressure of the hydrogen has to equal the pressure of the nitrogen. Okay? You can spell out the words. I think it's easier to just use the symbols, but you do whatever you're comfortable with. So I know the total pressure is 5 atmospheres from the problem, and I know that the pressure of the hydrogen is 3.2 atmospheres. This is asking you to find the pressure of the nitrogen. And because you are all gifted, wonderful students, you know that really all you have to do here to solve for x is subtract 3.2. And when I solve for x, I get my number, I get my units, and I draw a little circle. That's how easy Dalton's law is. The only way I can make a Dalton's law question tough is if I give you different types of pressure units and you have to all convert them to one. But Dalton's law are the type of questions you really, really want to see on a test because they're your guaranteed easy questions. Okay? The next thing in your notes talks about Graham. Graham talks about effusion. And you know from class, especially in biology, they usually talk to you about diffusion. So if I sit in the front of my room and I spray perfume, eventually that strong perfume smell that's here is going to flow all the way to every area in the room. And it's going to be a little fainter. It's not going to be as strong as it was up here. That's diffusion. Graham talked about something called effusion. And effusion is when gas seeps out of a tiny hole. For instance, if I have a balloon and I pop it, the gas is going to fly out of that tiny hole. And what he said was that the lighter you are, the faster you fly out of that hole. Okay? And he was using molar mass from the periodic table. So we would expect hydrogen to effuse a lot faster than carbon dioxide. Because when I look at their mass on the periodic table, hydrogen is a lot lighter. Okay, and that's all he said. Now, he took it a step further, and he came up with that crazy gas law that has fractions and it has square roots, but none of that bothers us hair flip because we are super chemists, okay? And I want to go over the example from your notes, which is the same example I did in class, just so you can hear it again if you need to. So we're looking at this slide here, and I know it's a Graham's law problem, and every time I see a Graham's law problem or any of these gas laws, I think it will serve you well if you just write the gas law out, because you can use that as your roadmap when you're doing the math. All right, the only thing I think that's really tricky about Graham's law is on this side of the equation you have A over B, and on the other side it's flipped and there's B over A. And sometimes that will stump a super chemist, but not you. Now, honestly, every time I was in college, every time I was in graduate school and I saw a Graham's law problem, I immediately wrote who I was making A and who I was making B. It doesn't matter who you choose, but you have to stick with it through the whole calculation, okay? I tend to list the first one as A because that just makes sense to me. So the first one listed in this problem was methane, and the second one is B, and that was an unknown. So I'm just going to put X there because it was unknown. I don't know what it is. So I look at my problem. Rate A. A is methane. How fast was the methane going through? In this problem, it's 1.5. Rate B. B is the unknown. How fast was the unknown? 4.73. Okay. Square root molar mass B. Well, I don't know what B is. B is my unknown. So that becomes my X. Molar mass A. A is methane. Methane has a carbon, which on the periodic table is 12, and it has 4 hydrogens. So 12 plus 4 is 16. Now, X in a fraction inside a square root. Nothing to it. Super easy. Anytime X is in a square root from algebra 1, you always have to square it. And when you square that side, you have to square the other side. So whatever you do to one side, you do to the other. So that pops it out of the square root. That's why that looks like that. Then you have to square these numbers. So 1.5 squared becomes 2.25. 4.73 squared becomes 22.37. That to me looks a lot more manageable than what we started with, all right? And I say it all the time. I think the easiest way to solve for X in these situations is to cross multiply. You would be amazed at what you can solve with just cross multiplying. So you cross multiply, you solve for X, you get 1.6. This molar mass, the units are going to be grams per mole. Shazammy poo-poo, I'm done. Now, the next part of your notes talks about mole fraction, okay? And mole fraction is like percentages. It's like that math you did in middle school before you got to algebra. You may have even touched on it in 5th grade. If I said, hey, I have 10 pieces of fruit and 3 are kiwi, what percent is kiwi? Well, the 3 over 10, which is the total, times 100. So mole fraction is that ratio before you multiply it by 100. Super duper easy. So if you look at the example from your notes, and I'm looking at this slide, you have a gas mixture. It has 5 moles of oxygen, 3 moles of water, and 12 moles of nitrogen. What's the mole fraction for oxygen? Mole fraction is denoted by a capital X. Okay, I always make it biggie, biggie. And because I'm saying oxygen, I put that down there to denote that anybody looking on my paper would say, oh, it's X, it's mole fraction, and it must be the mole fraction for oxygen. So oxygen in this problem, there's 5 moles. I'm going to put that over the total number of moles. So that's 5 plus 3 plus 12, which is 20. That reduces to 0.25. That's my mole fraction. That's how easy it is. Super duper easy. Now, the reason you learn mole fraction when you're doing gas laws is because when you're doing gas laws, let me cut this on, there we go. When you're doing gas laws, you can tie in mole fraction to partial pressure. If the mole fraction is 0.25, the partial pressure for that gas is 0.25, okay? They correlate. And in your notes, there was this formula that looked like that. This is the partial pressure of some gas. This is the mole fraction. We just talked about that. And that's the total pressure. So the example in your notes, and I am on this slide in your notes, says you have a mixture of 2 gases. The partial pressure of methane is 0.75 and the partial pressure of oxygen is 0.25. If I didn't give you the partial pressure of one of those, you could find it because all mole fractions have to add up to 1, just like all percentages have to add up to 100. So, what is the mole fraction of methane in the mixture? So I'm looking at methane. Methane a partial pressure of 0.75. So I'm going to put that in there. I'm looking for mole fraction. That becomes my X. And my total pressure, oh my goodness, I didn't give you a total pressure. But if I give you all of the partial pressures, you should be able to add those up and say, hey, that's the total pressure. So when I add up 0.75 plus 0.25, I get 1. X equals 0.75, okay? You will notice on your calculation sheets and on your quiz, I just went ahead and told you what the total pressure was, so you didn't even have to worry about it. But if I didn't tell you that, or you took a class later on, that's how you would calculate it. The last part of your notes just talked about ideal gases and their behavior and the kinetic molecular theory. And so we know that the kinetic molecular theory has 4 really big tenets, or 4 really big parts. And the first is that gas volume is negligible. And negligible was that fancy SAT word that kind of means it's not important, it's insignificant. If you look at the size of an oxygen molecule and you compare it to the size of this room, okay, it's negligible because it's so teeny tiny compared to the size of this room. Does it exist? Does it have volume? Absolutely. Is it important? Heck no. All right, the second part, gases are in constant random motion. Right now, as you sit in my room, as I'm standing here, gases are smacking me upside the head all over my body. They're moving all over the place in constant random motion. They're moving directly proportional to the temperature. If I heat up this room, those gases are going to zoom around really, really fast. And if I cool down this room, the gas speed is going to lower. So kinetic energy or gas speed is going to be directly related to the temperature. How hot is it? How cold is it? The hotter I make it, the faster they move. And then the last part on here is kind of physicsy, and you'll learn more about it next year in physics. We assume that gases, when they're bumping into each other, they're having elastic collisions. And what that means is when they bump, they don't lose any friction, they keep the same energy. Now, we know that's not true. We know when they bump, there's a smidgy poo of friction. But they're so tiny that their smidgy poo of friction, it's insignificant. It's almost negligible, our new world. Now, gases that behave like the kinetic molecular theory are said to be ideal. And we talked about this. There are no ideal gases anywhere in the universe. They can at times behave like an ideal gas. Sometimes I can be an ideal person, and sometimes I'm not, okay? But if I were to ask you, name an ideal gas, that's a trick question. There are none. But occasionally gases do behave in an ideal manner. Most gases do behave ideally most of the time unless the temperature drops really low or the pressure goes really high. And that concludes all of your notes for Unit 7. I hope this really helped you out, and I will see you in class, Super Chemists. Toodles poodles.